Well,
people are always talking about like, once this one thing is solved, it's all. I don't think that's right.
I hope people have not dropped the class. I don't know. I feel very, it's very it's very, I know, it's very disconcerting. I don't know. Anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and I thank you for these students. Just ask you to bless this time we have to study your creation, Lord. In your name I pray, Lord Jesus. Amen. So, I think I'm going to leave the exploration of the interesting, image, the conducting sphere with the charge outside and the method of images. I think I'll probably just assign that homework and let you guys kind of appreciate it there because, it's just a neat example pretty much. And if we do it in here, it won't probably help you with anything else we ever do. But I think it's neat to work through. So, but what we're about to do is, the solution solving. So what we're doing is we're solving Laplace's equation. All right, and so let me just kind of like give you a preview of what we're doing. Today, I'm going to do my level best to do at least one or two examples. If we get to two, it'll be amazing. Of the method of separation of variables for solving Laplace's equation. And so let me just get straight into an example because that pretty much is where it's at. So the example will illustrate the method, I hope. And so the example is this. This is example 3.3 in Griffiths. He says you got two infinite grounded metal plates lie parallel to the xz plane. All right. One at y equals to 0, the other at y equals to a. So if I draw his picture, I'm not going to draw his picture. I don't care about his picture. Fine, I'll draw his picture. I can't ever make mine. So you got these infinite conducting planes, all right, like so. All right. All right, so it goes on. And let's see here. So this is like the y-axis. This is the z-axis. And this is, right here's the x-axis, let's say. All right. Let's see here. X cross y is z. All right, good, right-handed. So these are infinite conducting grounded planes. Let me be a little bit more specific. Like, let me be explicit about the. So this is the conducting plane. This is the conducting plane. All right, and we're putting v equals to 0 up here, and this would be at y equals to a, and we're also putting v equals to 0 down here at y equals to 0. All right, and he further says that we're going to have v goes to 0 as x goes to infinity. All right, so we're looking to make that happen. But the one, like everything's 0, right? Except right here. All right. In this region here, we're going to put v equals to, according to Griffith's notation, v naught of y. This is for x equals to 0, all right? So, of course, my picture is somewhat limited. I mean, this goes on and on, all right? And so I guess maybe the first thing to do with a horrible picture like this is to suppress the z direction and just be, oh, seriously? Yeah. Haha. All right. So here's a entirely more useful picture. Why? So we've got, basically we've got v equals to 0 at y equals to a. We've got v equals to 0 down here. And then over here, right, we've applied a voltage on that boundary right there, which is a function of y. Right? And to be clear, no charge in here, right? The density is 0 between the conducting plates. So what does that mean? What do we face? Well, we face Laplace's equation, right? So we have to solve the Laplacian equals to 0 let's give the space a name. I guess we've been calling it, I really hate using that V. Let me call it something. What do you guys want to call this region? Let's call it script. I think we can use script R. We don't use that for anything else. R for region, right? We're trying to solve this in R. And we're given boundary values, right? For the boundary of that region. So it seems like there's hope, right? That if we can find a solution, then what? Well, the uniqueness theorem we had last time says we've done a good thing, right? We found the solution, you know? So how do you find it? How do you construct a solution for something like this? Have you guys seen this before? Do you do this math? I mean, you maybe in like your heat course or something, or do you guys solve Laplace's equation in like heat transfer? Okay, so this should be very familiar to you. If you haven't had the heat course where you solve the temperature diffusion equation by separation of variables, then this should be dark magic. But it's magic we'll learn together. So here we go. So what we're up against is, partial squared v partial x squared plus partial squared v partial y squared equals to 0. And, okay, fine. To be fussy, partial squared v partial z squared, right, is equal to 0. I mean, it's a three-dimensional problem. That's what we have at the outset. All right? But by symmetry, there is no z dependence because the boundary conditions are the same. You might be like, well, you're doing something over here on z. Yeah, but it's only got a y dependence, you see? So there is no z dependence to the solution. So we can drop back to two dimensions, yeah?
So the planes do extend all points.
Yeah. It keeps going. My picture is just, that's all I can draw. So like this comes out at you and it goes back in. So it's an infinite half slab, I guess. Okay, so we can just suppress that, and we're just looking at partial squared v partial x squared, and that notation is really obnoxious. So let's try vxx plus vyy is equal to 0. This is the equation we have to solve because we can see v is just a constant, right? I mean, the z component, there's no z dependence, that's what I'm trying to say. Symmetry, v is equal to a function of x and y alone, all right? There cannot be a non-trivial z dependence, so we can just look at the x and y. All right, so then this is where it gets interesting, is we propose solution of form v of xy equals to x of x, big Y of y. So we suppose that we can write the solution as a product of functions of x and y. All right? Now that's kind of a wild conjecture, but let's see where it takes us. So if that's the case, then Vxx is equal to x prime prime of x times y of y. And Vyy is x of x y prime prime of y. Now I'm just writing v of x and of y for the sake of like telling you what I really mean, but let's not do that so we can write less, yeah? So x prime prime y and x y prime prime. Where of course the primes on x's are x derivatives and the primes on y are y derivatives. All right? And then you just take these, plug it back up in here. Lo and behold, we've got ourselves a x prime prime y plus x y prime prime equals to 0. From here to here. Just plugged in this and that for this and that. Now, next move, we're looking for non-zero solutions. Obviously, 0 is a solution, right? 0, like v equal to 0 solves everything, but it's not what we're looking for. Since it's not what we're looking for, nothing is lost by dividing by the solution. So if I divide by v, this gives me what? This gives me x prime prime divided by x plus y prime prime divided by y equals to 0. Dividing by x and y, cancel the y, cancel the x. Now, of course, this I can trade for x prime prime over x is equal to minus y prime prime over y. All right? And we can say that that must be equal to some genuine constant. Let me call it I don't know. Oopsilon? Oopsilon it is. I'll allow it. Ah, yes. Why does that have to be a constant? Well, let's think about this. This is a function of x alone. That's a function of y alone. Right? In other words, if I partial differentiate this with respect to y, I get 0. If I partial differentiate that with respect to x, I get 0 by assumption of the construction. So if I differentiate oopsilon by x or by y, either one, I get 0. Therefore, oopsilon's a constant. Another way of saying this, the only function which is both a function of x and a function of y is the constant function, right? Like we talk about functions of x and functions of y and functions of t. Which functions are common to all of the different kinds of functions? Like f of x equals to 3, right? F of t equals to 3. You know, f of z equals to 3. These are all the 3 functions. The constant functions are shared by functions of different variables. Anyway, so that has to be a constant. All right, so then we're trying to solve x prime prime and you say oopsilon, but I say minus oopsilon. So x prime prime plus oopsilon x, what have you done to me, equals to 0. And we're also trying to solve y prime prime minus oopsilon times big Y equals to 0. See, so the separation of variables problem has led us to this pair of ordinary differential equations for big X and for big Y, you see. Now, let me remind you then what the situation is here. We need V of what? X comma 0, right? And that would be x of x, y of 0, right? We need this to be 0 for all x. We also need v of x comma a to be, by the way, x of x, y of a, to be equal to 0 for all x, right? For my boundary conditions. So since this holds for all x, I can extrapolate from this that what I really need is y of 0 must be 0 and y of a must be 0. So these are what I would call boundary conditions for big Y. All right? Those are the boundary conditions big Y must solve. All right? Now, so in principle, as you think, have you had differential equations? Okay. So maybe you remember the story. Constant coefficient, there's 3 different cases to think about here. Either the upsilon's positive, it's negative, or it's 0. If it's positive, sines and cosines. If it's negative, cosh and sinh. And if it's 0, you get a linear function in time. Well, excuse me, x. So as I look at these, what that makes me think is I should probably, to give the full story here, I have to consider all the different possible cases for upsilon.
Zero's quadratic.
Yes, zero's quadratic. So let's sort through those. All right. So like case number 1, we'll start with upsilon equal to 0, right? So I'm solving y prime prime equals to 0. That means y of y is like ay plus b, right? But we know y of 0 is b, and y of a, ooh, bad choice of letters. A1 and B1, haha, fixed. Is A1A plus B1, but that's 0, which then implies that A1 is also equal to 0. All right, great. So after a second, you see, oops, can't have that, right? Which is not surprising, right? We can't have a line in y which starts and ends at 0 at different values of y. Of course not. There's no solution to be found here. Case number 2 would be, I'll try to do the boring cases first. My intuition here is that if upsilon is positive, we're not going to get anything. So we're going to say it's equal to beta squared because it's greater than 0. So what I'm doing here is just, I'm introducing this squared variable so that I don't have square root of upsilon over the place. If I do this, then what I'm looking at is y prime prime minus beta squared y is equal to 0, which tells me that my solution, generically, is y of y is like, let's say, c1 cosh beta y plus c2 sinh beta y. Now, maybe you only did exponentials in your course. If so, you were shortchanged. You should demand a refund. Dr. Wang did not do cosh and sinh. Is that the truth?
Yeah.
Wang doesn't do cosh and sinh? Not cool, man. Not cool. I'm going to have to talk to him. Anyway, but if I do, it's going to be a conversation about the organ harvesting in China, which is interesting. Very interesting.
Organ harvesting.
Exactly. What organ is organ harvesting? I mean, so it seems like in this country, there's a lot of people who are like being unnecessarily killed for the sake of like harvesting organs, but We think those people are mostly dead, so it's kind of okay. That's what I've been reading, give or take. But I don't think anyone's doing it. Most people, it's not like rich people are doing it to try to extend their lives or something, right? It's just, at worst, maybe you could attribute the motives of, profit motives of hospitals or something like that, whatever. In China, on the other hand, if I understand the stories correctly, bad things are happening in terms of people going to China, getting organs, and then, they just, if you need an organ, you just go find a person that matches and then end their life, and then you got their organ, which seems kind of unethical. I don't know, but I don't think I should get in trouble for saying this on YouTube. I don't know, but who knows? We'll find out. But anyway, continuing with the physics. So this is the solution, and we have nothing defined here, though. You see, because y of 0 is c1, because cosh of 0 is 0 and sinh of 0 is 0, so c1 is 0, and then y of cosh of 0 is 1, so that gives me c1 times 1 is 0, but sinh of 0 is 0, so this equation, the boundary condition becomes c1 is 0. Y of a, thank you for correcting, c2 sinh of beta a, all right? But the thing with sinh is only 0 at 0, and if we're assuming beta is not 0, and we are, right? A and beta are both non-zero, that means sinh of beta a is non-zero. And as such, by process of elimination, C2 must be 0, since this is equal to 0 by the other boundary condition. Lo and behold, nothing to see here. All right. Now what Griffiths almost certainly does is not show you this and just write down the interesting part, if I'm guessing. Which is what I would do too if I was smarter. But I wanted to show you the logical process, which is there are cases to consider. The other case is that upsilon is minus beta squared, you see. So it's either 0, positive, or negative. And if it's negative, we can write it as minus a square. And if we do that, then we're up against y prime prime plus beta squared y equals to 0, which tells me that y of y is c1 cos beta y plus c2 sine beta y. All right? But now I apply the boundary conditions once more. So apply the boundary conditions, what do we get? We get y of 0 is c1 is 0, and we get y of a is c2 sine of beta a equals, oh man, it's all 0 again, right? Except sine is not sinh, right? Sine is not sinh, and there's a way around here. See, we can have sine of beta times a is equal to 0 for beta a equals to n pi for any 1, 2, and so forth, right? I mean, technically speaking, for any integer that works. But if you think about it, because we're building a solution as we are, it suffices to just look at positive integers. The 0 solution, we already got rid of. That's the constant solution. We don't care about that. So we start at 1. That's the interesting part here, right? So look at this. So apparently beta is actually got to be n pi over a. Boundary conditions are very finicky. Like when we, in differential equations, we solve hundreds of problems, right? But they're all initial value problems. We solve them, we fit initial conditions, we don't think anything about it, right? If you write down a differential equation, it has solutions as long as the coefficients are continuous, right? But these are not initial value problems. These are boundary value problems, which means that you're specifying values of the function you're looking for at different independent inputs. And there's no guarantee that there's any solution that's non-trivial and interesting to these. As we saw, only the zero solution, only the zero solution. All of a sudden here, we learn, well, there are non-trivial solutions, but they come with strings attached. Upsilon can't just be anything. Upsilon has to be what? Well, it's minus beta squared, which apparently is minus n squared pi squared over a squared, yeah? So we went looking for a solution. We just found infinitely many. That's good. And so the solutions have the following form. Y sub n of y, something like, sine of beta y, but beta was n pi y over a, right? So there you go. That's these are sometimes called eigensolutions, right? And it's easy to see that that satisfies the boundary conditions, right? It's good?
We don't have a constant up front.
Don't need it. These are, we'll put the constant back in a second. So then, how about I agree with you, the constant needs to come in at some point, but I don't know what Griffith's notation is. I'm not even looking at Griffith's notation. Let's make our own, okay? So, yeah.
So necessarily the capital X has to have a sinh cosh rule.
Oh, okay, so then, yes. So you're like, now see, this, we don't get to go through the story again for X because X and, you see, look up here, from the start, from the get-go, the fate, right, of X and Y are conjoined, right? So what we got? We've got X prime prime, right? Plus upsilon, which is apparently minus n squared pi squared over a squared times big X equals to 0. Well, that has solutions. Xn of X equals to, like, let's say, a sub n cosh of n pi x over a plus b sub n sinh of n pi x over a. Because this is the lambda equals to like plus or minus n pi over a characteristic values. So it gives us cosh and sinh solutions. If you like exponentials, you in Dr. Wang's class may have written like c1 e to the lambda x, plus c2 other lambda e to the x, but you can regroup those in cosh and sinh, and it's better, much better to do that for the purpose of, you do not use exponentials for boundary value problems. It's just bad. It adds another level of algebra. This, using cosh and sinh makes it like 30% easier, I think. I don't know. Okay, great. So let's put it all together. We have found that this voltage allows this solution of, like a sub n cosh n pi x over a sine of n pi y over a, right? Plus b sub n sinh of n pi x over a sine of n pi y over a, right? And any choice of a or b solves the boundary conditions that we've studied so far, which is only half of the boundary conditions, right? What about the other two, though? What do the other two boundary conditions have to say about what we're doing? The voltage goes to 0. Okay, so like the next thing we do, guys, is instead of doing this, here's what we're going to do. Watch this carefully. We're not going to do this. We're going to just go, well, if one of them works, let's just take and throw them all together in one big old solution. See, because we've got linearity, right? If one solves it, then the sum of them also solves it, because Laplace's equation is linear. So we can take an infinite sum of solutions, is again a solution, right? And so now we just need to figure out what the choices of the a sub n's and the b sub n's have to be to make it work. It's kind of like infinite undetermined coefficients, right? You can think of it that way if you like. Now, yeah, I think we could make a good use of that infinite boundary condition, which was what? What did we say? V of x comma y goes to 0 for as x goes to infinity, was it? So whoa. Oh man. Am I wrong? All this talk about Cauchy and Cinch, maybe I just set myself up for the fall. Oh no, he uses exponentials, and now I see why. Son of a gun. Rats. The reason to use exponentials here is because, why?
Oh, right. Because each of them has a positive value.
Yeah, so if I use exponentials, a sub n, e to the n pi x over a, plus b sub n, e to the minus n pi x over a, right? Man, son of a gun. It's easily fixed though, check this out. Exp, minus. These are logically the same, but let me put some tildes on these to just, they're not the same constants obviously, right? But it is possible to rewrite the solution. Rats, man, anyway, I'm sorry guys, this is where if I was teaching 2 classes rather than 4, or what, how many classes am I teaching? I can't remember. Enough, but sorry, poor planning on my part. We should have used the exponentials because then this boundary condition is easy to implement. The trouble with my previous formulation is both of these go to infinity, so it's really hard to apply this boundary condition in a nice way. But now, you know, we need what? We need a sub n is equal to 0 for all n in order to get this boundary condition. See, because that automatically goes to 0 as x goes to infinity because it's a negative exponential. So we're at peace with this boundary condition as long as we don't have these guys. So now we have reached the v of xy equal to the sum n equals 1 to infinity of b sub n e to the minus n pi x over a sine of n pi y over a. All right. Now there's one boundary condition still standing, isn't there? Right? The one boundary condition that we have not yet applied is what? We also have v of 0. What is it? I can't remember. Man. Sorry, guys. Yeah, that's x equals to 0, right? V of 0 comma y is equal to v naught of y. What is v naught of y? Well, that's a given, this is a given function of y in this example, in the arbitrary sense of being given, all right? So, but the point is that that has to be equal to the sum n equals 1 to infinity of b sub n sine of n pi y over a, all right? And then this is where we need to use Fourier's trick, all right? Fourier's trick says, if you want to solve this kind of thing, what you do is you multiply by, let's see, we're going to integrate, I believe, from 0 to a. Integrate both sides from 0 to a after we multiply both sides by, let us say, the sine of n pi, not n, I need a different letter. Let's say like j pi y over a, all right, dy. The integral. So then, on the other side, what I'm going to do is I'm going to pass the integration inside the summation, and I'm going to pull the b sub n out, all right? So I've got like the sum, n equals 1 to infinity, pull the b sub n out of the integration, and I'm up against integral of sine of n pi y over a sine of j pi y over a dy.
Bounds are also the same.
Yes, bounds are the same. So I'll do that over here. So how do we do that center? Integral from 0 to a of, sine of n pi y over a times the sine of j pi y over a dy, right? So the product of two sines gives me what? It gives me like minus 1/2 times the sine of, I want to say n plus j times pi y over a minus the sine of n minus j times pi y over a. dy, all right? This is correct up to like a plus or minus. I could be wrong, okay? I haven't double checked, but. And then the thing is, the way that integrates is, there's a half that pulls out, and we make a substitution, right? So you got like a over n plus j pi cosine I guess I need another minus for the cosine integral, right? And then how's that work out?
N and J are integers.
Yeah.
So if y equals a, you'll have n integer times pi.
Yeah, 1/2. I have a times the cosine of n plus j pi over n plus j pi minus a times the cosine of n plus j pi over n minus j pi. That's from the upper bound. And from the lower bound, I get minus 1/2 a over n plus j pi strength leaving body, ability to calculate, waning, must drink coffee. Poor planning on my part, should have had coffee before class. Let's see here. Now, what's the cosine of, you guys know what these are?
1 of n plus j and even minus 1.
But what's a formula? How about minus 1 to the n plus j? This is minus 1 to the n plus j. Was I supposed to have n minus j on this one?
Yeah.
That probably matters. Anyway, this is 0. As long as for n not equal to j, this is 0.
Because n plus j or n minus j have to both be either even or odd.
Yeah, I mean, if we sort through this properly, if I have a little bit more juice, we can show this as 0, which is to say that sine of different arguments, they're orthogonal functions. See, like, you define the integral, like the inner product of f and g in this context, something like integral from 0 to a, f of y, g of y, dy. And if you define this as kind of like a dot product, with that sense, these are orthogonal functions because they're perpendicular. If I could do the calculus, we work it out to be 0, except when they're not 0. When these are equal, this calculation is bogus. When they're equal, we just have what? So if they're equal, we're up against the integral from 0 to a of sine squared. I can't read, n pi y over a, right, dy, which is the integral from 0 to a of 1/2 of 1 minus the cosine of 2n pi y over a dy. And that integrates to y over 2 minus, a over 2 times 2n pi times the sine of 2n pi y over a. Mercifully, the sine term goes away because we get a multiple of pi into sine, or 0. So the sine term is dead, and we're just left with the constant term, which reveals to us what? So yeah, that just, you say a over 2? Is that right? Yeah. Which, when we go back to, if you believe me, what I'm trying to tell you is, when we actually carry out the integration, in the upper left-hand corner, if you believe my calculus, and please do, this works out to a over 2 times the Kronecker delta of j comma n. And again, there's a bit of a gap here. I haven't showed it 0, but when I finally catch up in my note writing, I will have the gory details there. Maybe I don't have time to go to the math party this weekend. I don't know. So you guys see what happens there then? if I'm right, if that integration works out to, it's either 0 or it's a over 2, then this business right here is equal to what? B sub j, right? B sub j times a over 2. And so what that tells me then is that my b sub j is equal to, I can solve for the b sub j. So b sub j is equal to 2 over a integral from 0 to a, the given function of voltage at the boundary, v naught of y, times the sine of n, not n, but j in my current language, j pi y divided by a dy. So then if we put that, so like this, so that right there, and the voltage at xy, z, I'll put the z back in now, it's the sum, you know, if you like, you can use j equals 1, I'm going to use n. We don't have to put a j there, we could put an n there, but I'll do n. N equals 1 to infinity of b sub n e to the minus n pi x over a times the sine of n pi y over a. That is the solution to this example. So the solution is an infinite series of exponentially damped sines in y by, you know, factors in x. It makes sense that x is dying, yeah.
Assuming it's separable.
Assuming it's separable. Well, you know. Does this satisfy the boundary conditions?
Yes.
And if the solution to the Laplace equation exists, is it unique?
Does it solve the Laplace equation?
Well, yeah, I mean, that's how we got here.
All right.
So if you believe the mathematical sleight of hand I just did, then good, okay. I mean, the issue, of course, is the issue, and the reason that differential equations book at this point will tack the word formal on it is because we haven't actually proved that these converge, right? There's a question of whether or not we actually have convergence of the series, but in fact we do, if you are willing to calculate. Okay, if you don't mind, I'm going to switch that j to an n so it's not weird. Yeah? Let me now foolishly go look at Griffiths and see if we got the same result. Page. Come on, man. Out with it already. Yes, I believe so. His equation 3.34 on page 133 is what we just have derived. He's used a C rather than a B. So equation 3.34 is this, but his Cn is my Bn, all right? So to make further progress on this, we have to actually give specific voltage functions, right? Now the way I like to, an easy way to make this problem like reasonable for an exam question is to make it so that you don't actually have to like do these integrals. So let me show you what I mean by that. Like if Okay, so the whole point of the Fourier trick is to find it's a means to find the Fourier decomposition of the boundary condition. So like, what I'm trying to get at here is if we're given v naught y is already the appropriate kind of Fourier series, we don't actually have to do the integral. We can just compare coefficients. Like, for example, so notice that we have, from our red equation over there, we had, this is just from the boundary condition. Boundary conditions got us this, right? Let me just remind you guys. We had found our way to, this is equal to the sum, right? N equals 1 to infinity of, what was it? B sub n sine of n pi y over a, right? Okay? That's just a blank template to capture those kind of boundary conditions, right? I'm almost done. We'll stop soon, guys. I'm sorry. So check it out. If v naught y, right? Suppose it's equal to 67, the sine. Oh, that's right. You guys don't care about that. Let's see here. 42. Thank you. That's more your generation. 42 sine of, I don't know, 13 pi y over a, all right, plus 16 sine of, 8 pi y over a. I'm refusing to make this problem less annoying. We give a value for a like 1, all right? So if that's the case, the beauty of the Fourier series mathematics is that since the signs of different arguments are linearly independent, the only way that those two can be equal is if they have matching coefficients. Now, the mechanics of that is Fourier's trick. If we multiply this on both sides by sine of an arbitrary value and then integrate from 0 to a, if we do the calculus, we will find that the coefficients have to match because the integral of the product of the sine gives us a Kronecker delta, which is effectively like the dot product for these functions. But anyway, getting to the point, I can read from this that b sub 13 is 42, and b sub 8 is 16, and then that allows me to write my answer down as simply 16 e to the minus, where was he? Oh, 8, right? E to the minus 8 pi x over a sine of 8 pi y over a plus 42 e to the minus 13 pi x over a sine of 13 pi y over a. And that is explicitly the solution to Laplace's equation on the infinite slab, subject to the boundary condition I just made up, namely it matches 42 times that sign plus 16 times that sign. No integration required. We just set up the boundary conditions and use some like known theory of trigonometric series like matching coefficients. Yeah. Generally though, integration is required. And I think the example in Griffiths on page like 133 to 134, he actually does it for something, a little bit interesting, like, what is it he picks here? He just does a constant potential. So he actually has the solution, if you put v naught equal to a constant, the integrals are still interesting, actually. So anyway.
Doesn't that violate the boundary conditions?
No, you can have v naught equal to a constant. That's a function of y. Just here.
What about the edges?
It's insulated.
But v naught is 0 at the top.
Yeah, well, we face those kinds of discontinuity at the edges, yeah. You're like, I thought you said that the voltage was continuous everywhere. Well, yeah, except for where the boundary conditions are meeting discontinuously. Don't harsh my mellow. I don't know. I mean, yes, I hear you. Nevertheless, this is what we do. Because yeah. Look, he has a graph. That makes it real, right? See? There. That's the constant potential graph. I'm not sure what this graph means. Oh, he says that the vertical direction is V naught over V. I guess that's X, Y, and then the vertical is just like the value of the voltage in the, Yeah.
My favorite method.
All right. So what's next is to try I'll probably probably the next thing I'll do will be to, well, he's got like another Cartesian example that maybe we should do, but past then he starts looking at problems with either spherical or cylindrical symmetry and how that works out. And it turns out that we need to study some more theory of orthogonal polynomials to make progress on it more deeply, namely the Legendre polynomials and so forth. So the mathematics and theory in this chapter gets kind of deep all of a sudden and very mathematical, but I'll do my best to communicate it in a reasonable amount of time. So anyway, thanks guys.